All right, radical and exponential equations. So we've been dealing with radicals and exponents, but now we're actually going to set them into equations and solve. And so if you look at the first example here, a couple of things we're going to look for is, can I simplify it first? Can I combine anything first? You'll notice that you have an index of 3 on both of these, but it's not like moving it over is going to help right now because I don't have the same number on the inside. And so the first thing I'm going to do here is I'm going to see, well, can I simplify this? And maybe that will help me out. And it does. This is the cubed root, so I'm looking for a group of 3. So I have 2x minus that 2 that can come out. This 2 will stay in. Equals 10 cubed root of 2, all right? And so then I am going to move all of my radicals to one side, kind of like I would if I had variables of 2x and 10x or something like that. So I'm going to move this over to the other side with addition. I'm going to say 2 cubed root of 2, 2 cubed root of 2. And then I'm just going to add them. So over here they cancel. I'm left with just that 2x. Over here I have 10 plus 2, that's 12 cubed root of 2. And then my last step, like in any equation, would be to divide by 2. And so once I do that, I am going to get 6 cubed root of 2. And that is as simple as I can get it. I can't simplify that radical anymore, so that is my answer. This next one's a little bit different because I have x's and then I have these radicals, right? And so with something like this, I want to move just the radicals. So if it's just a radical with no variable, I'm going to move that to one side. And anything that has a variable, even this radical, I'm going to move to the other side, okay? And so that's my first step here. I am going to move this 5 square root of 2 over with addition. All right. And then I am going to move this x square root of 2 over with subtraction there. All right. And what I have left on this side, I have x minus x square root of 2. And on this side, I can actually combine them. I have 3 square root of 2, 5 square root of 2. So that's 8 square root of 2. All right. Now here's where it's a little bit different. I have an x and an x in each of these. I am actually going to factor it out. Just like if I had something that I could take out of a group, right? I'm going to factor it out. Both of these have an x, so I'm going to put an x on the outside. X divided by x is 1. X squared root of 2 divided by x is just the square root of 2. All right? And now between these two is just multiplication. So I'm going to divide both sides by this entire group. I'm going to take that group and divide both sides by the group. All right? So I'm going to divide this side by 1 minus the square root of 2 and this side by 1 minus the square root of 2. It will cancel here. Now for this one, I have my x completely by itself. That's going to equal 8 square root of 2 over 1 minus the square root of 2. But I have a little bit of a problem right here. I do not want to leave a square root of 2 in the denominator. So just like on our last section, what we just quizzed over, I am going to get rid of that by multiplying by the conjugate. So I'm going to multiply the top and the bottom by this guy right here. All right, and I'm going to distribute that top. 8 square root of 2 times 1. 8 square root of 2 times the square root of 2 is just 8 times 2. The square root goes away. On the bottom, remember I'm multiplying conjugates. So it's the first one squared, which is just 1, minus the second one squared. Well, when I square a square root, I get what's inside. So that's just the 2. So on the top, I have 8 square root of 2 plus 16 over negative 1. Now, I will never leave a negative 1 on the denominator. I could just put it through to the numerator and not have a fraction at all. So for this one, I am actually going to simplify it by putting that root, putting that negative through to each one of these on the top. So that 8 square root of 2 is going to become negative 8 square root of 2. That positive 16 is going to become negative 16. And that is my answer there. A radical equation is an equation that contains a variable in a radicand or has a variable with a rational exponent. So if your variable is inside the radical, it is considered a radical equation. Or if your variable has a fractional or decimal exponent, it is a radical equation. Okay? So what we've been doing so far had x's in it, but they were on the outside. So they were technically just regular algebraic equations. Even though you had radicals, those radicals were just coefficients, right? In this case, the radicand, or the number inside the radical itself, has a variable. And so we're gonna have to manipulate how to get it out. So if it's a square root, you're really going to try to get the root by itself, and you're going to square both sides. Because if you square a square root, it's going to go away. If you have a cubed root, you want to get the cubed root by itself. Cube both sides, because if you cube a cubed root, it goes away, right? Same thing like this. We have something to the fourth power. Whatever your power is, if you raise it to that power, you will get rid of it. So whatever your index is, if you raise that to the power, it's going to get rid of it. All right? And so the reason this works is we have square root. We can rewrite it as 1/2. You may also see it as 0.5. These all mean square root, okay? If I were to take this to the second power, it would get rid of my fraction. If you see to the 1/3, that is the same thing as a cubed root. If you see to the 1/4, same thing, or 0.25, that's what you'll see. That's the same thing as the fourth root. And so you're basically raising it to the denominator or to the index to get rid of that altogether. So it's true of any root. No matter what your root is, if you raise it to that power, you're going to get rid of it. So let's look at some examples. All right. So really my first goal is to get the radical completely by itself. So to do this, I'm going to first move anything that has nothing to do with the radical. In this case, I would add that 2 over. Eliminate that. I have 3 square root of x plus 4 equals 12. And then divide both sides by 3. Not going to last. All right. So that cancels. I have x plus 4 in the root. I have 4 over here. What is my index here? So my index is 2, which means that's the power I'm going to raise both sides to. All right, on the left-hand side, how that helps me is raising an index of 2 to a power of 2 gets rid of the radical altogether, and I have just this guy right here. On the right-hand side, I have 4 squared. That's just 16. And then I have a rather simple solution here. X is going to equal 12. You do want to make sure these work. You can have what's called an extraneous solution, something that works when you first get it, but if you plug it back in, it causes a problem. For example, if it causes a negative in my root, this would be a problem, right? Even though getting rid of my root allowed me to solve an equation, if plugging it back in causes an actual problem in real numbers, it cannot be an answer. So you do want to do a quick check of these. You want to say, well, that's 12 plus 4 minus 2 equals 10. 12 plus 4 is 16. 3 squared is 16 minus 2 equals 10. Square root of 16 is 4. 3 times 4 minus 2 equals 10. That's true. 12 minus 2 equals 10. So you do want to double check and make sure that you haven't created a problem with your answer when you get something like this. So conceptually, this is really the same thing. If you look at example 3, I will say this is one where we have to check our solutions and we'll figure it out. But this is a root of 4 in my radical, or in my exponent. And so I can subtract that 5 over, and I will get x to the 1/4 equals negative 2. So just like a 4th root, what do you think I'm going to raise this to?
4th power.
Yeah, to the 4th power. So on the left-hand side, that x is now by itself. Negative 2 to the 4th power is, what, 16? So according to this, my answer is 16. I have a little bit of a problem, though. When I test this, all right, you're going to double check this and see what happens. And so if I were to plug this in, I would say, well, 16 to the 1/4 power plus 5 equals 3. Okay? 16 to the 1/4 power. Well, that's the 4th root of 16. What is the 4th root of 16?
2
It's just 2, not with real numbers. So it's just 2 plus 5 equals 3. That is not true. So some people will say, yeah, it's 2 or negative 2. That's only when a variable is involved. When you are plugging in just a number, if I said, what's the square root of 16? You would say 4. If I said x squared equals 16, x could be 4 or negative 4. Do you see the difference? If they ask for the square root of a number, just in general, you assume the root that matches what the number is. The square root of 16 is 4. It is not negative 4. Okay, so if I just have something like this, that will always equal 4. It will never equal negative 4. If I have something like this, then I have a variable involved. I have something squared equals 16, and that could be 4 or negative 4. That is a difference, okay? So this does not work. This is not a solution. We have a problem, okay? When I plug that in, I get a false statement because I created this negative right here, all right? And so in this case, you would say no solution. No solution to that guy, okay? So there is a tendency, because we have been solving with variables so long, that you just assume, oh, well, the square root of 16, I could say that's 4, I could say that's negative 4. No, you cannot. When you are plugging it back in and doing straight algebra, you go back to what you would do when you learned order of operations. When you learned order of operations and someone asks you what's the square root of 16, you would say 4, right? So there's a difference between this and this. Okay, there's a difference between those. If you have a variable squared, yes, you have to consider the positive and the negative root. But if you are just taking the root of a whole number, you do not consider a positive and negative root when there's no negative in there, okay? So in this case, when you check it, you have what's called an extraneous solution. You're going to see those instructions in your homework, and you're going to see that on my worksheets. It's going to say solve and check for extraneous solutions. What that means is solve the equation, and then you need to plug it back in and make sure that solution actually gives you a true statement. If it does not, it is considered extraneous, and that is not a solution to that problem, okay? So because I only had one answer, and that answer was extraneous, I actually have no solution for this particular one. An exponential equation is an equation in which a variable occurs in the exponent. So we have had the variable inside the radical. Now we're going to look at what happens when the variable is inside the exponent. So in this case, we're going to, as we go on with Algebra 2, we're going to have other ways to solve exponential equations. But when you have like bases, so you have to start thinking about a base not just as what you see, but what it could be if I rewrote it, okay? So you need to start recognizing that something comes from the same number base. Like for example, if I gave you 1,000, hopefully all of you would know that would be 10 to some power, right? Because you can look at it and say, well, it's a 1 with zeros. It's a base 10, okay? And so 10s are really easy to see what the base is, because it's a 1 with zeros if it's a base 10. Or it's a decimal with zeros in front of a 1. One or the other, right? Those are your base 10s. But when you see something like this, you need to start recognizing, hey, they come from the same base. So if you don't recognize it, you need to be really good at factoring. If I were to look at these two, I would say, oh, I have a base 4 and a base 32. I can't do anything. Well, that's not exactly true. 4 comes from 2. 32 also comes from 2 if I were to rewrite it. Okay, so I can actually rewrite these and I can say, instead of writing a 4, I'm going to write that guy as 2 squared to the x. Okay, and instead of writing a 32, I am going to write 2 to the 5th power. Okay, and so if you don't automatically know that, you may have to do the factor tree. And then you can say, oh, 4 is 2 and 2, that's 2 squared. Oh, 32 is going to be 2, 2, 2, 2, 2 when I get it in primes. That's 2 to the 5th power, okay? And so use your properties of exponents. When you have a power to a power, you multiply them. So this is actually 2 to the 2x, and this is 2 to the 5th. Anytime you have exactly the same bases to a power, your powers are equal, okay? That's what that rule just tells us. So that means that that 2x will equal that 5. So I can just say 2x equals 5. Well, that's rather simple. Divide both sides by 2. X is going to equal 5 halves. And that is my answer. 5 halves is my answer, okay? So this is when I have a variable in the exponent position. I am going to look for ways to rewrite these. What do you think my base is on B? If I look at this one, this is easy. I can rewrite 25 as 5 squared. So that is 5 squared to the x power. 125 is 5 cubed. But what am I going to write if it is in the denominator? I'm not going to write a 3 here. I'm going to write what? 1/3 is the root. 1/3 is the root. What puts it in the denominator? A negative puts it in the denominator. Yep. So I can, if I see something in the denominator that is a base of that same number, I'm going to just put it to that power with a negative. A negative puts it in the denominator. And so then I'm going to use that same rule, power to a power. Well, that is 5 to the 2x equals 5 to the negative 3, which means that my exponents are equal. 2x equals negative 3. So x here is going to equal negative 3 halves.